Any questions? Yes, Muhammad. Go ahead, Muhammad.
دكتور الله يعطيك العافية.
هلا محمد.
دكتور بس بدي أسألك شغلة عن الستاك بوينتر. لما أخزن الريتيرن أدرس، لنفرض إنه كنت أنا عامل initialize للستاك بوينتر على مثلا $sign 1500 تمام؟
Okay. So this is the memory, and this is the stack pointer is now pointing to 1500 hex. Okay.
تمام. بدي أخزن الريتيرن أدرس، يعني بدي الكونتنت أوف بي سي أعمل decrement by 2 أخزن، ولا ال 1500 بخزن فيها أول أدرس؟
هلا 1500 you decrement by 2 because you want to store 2 bytes. So
100%
it will become $14FE. So now you have 2 bytes. Let's say that the program counter is let's say whatever 2000.
Okay.
So this is the address of the instruction to be executed after we come back from the interrupt or after we come back from the subroutine. So what will be in the stack? It will be, you will have
2000.
00. The most significant byte goes to the low address, and the least significant byte goes to the high address, which is 14FF, like this, and the stack pointer will be updated automatically.
اوكي راح يصير 14FE مظبوط؟
14FE, yes.
طيب سؤال ثاني إذا سمحت.
Yes.
دكتور بالنسبة لللوك IF صح إحنا هي depends على اللوك بت؟
Yes.
امبارح يزن سألك حكى لك في instruction كتبناه مشان إنه ويت عبين ما يصير إنه السيستم ستيبل.
اوكي.
هسا أنا بقدر أعمل ست لللوك IF أنا في بالسبيشال انستراكشن؟ ولا لازم ما بقدر صح؟
No.
Okay.
This flag, I will talk about it today.
Okay.
Okay.
Thank you, doctor.
Okay. Okay.
دكتور عادي بس سؤال بسيط.
بسرعة.
Okay. Just a quick question. بخصوص دكتور assigned numbers. The only different إنه آخر bit بتكون إذا كان negative بتكون 1 right وإذا كان positive بتكون 0 صح؟
Yes.
اوكي بس ما بتدخل هاي البت باي حسابات بالاديشن او السبتراكشن. It's just sign صح؟
لا, we work with it as if it is part of the number. يعني when you add two signed numbers you add with the sign.
اوكي.
شفت هاي؟
بس انا بكون عارف ضمنيا انه البت الاخيره it's for sign.
Yes. It tells you whether the number is positive or negative, but when you do the arithmetic you need to you include it in your calculations. Okay?
تمام.
Okay. So let's continue with what we have left from chapter 6. Last time we started with the second part where we are still talking about the CRG block, which is the clock reset and clock generation and reset block. And we talked also about the interrupts in the first part. So we had a very, we talked about different stuff related to the CRG block. And basically the CRG block is related to the generation of the clock, whether it is, or the generation of the E-clock, which is used to execute instructions, and the core clock, which is used to run the peripheral devices. And this clock can be taken from an external crystal oscillator or from some external function generator or clock generator. And the incoming clock, as we said, can be scaled by a special block inside this CRG block, which is the phase lock loop block, where we can scale the clock that is coming in and use it as the system clock, which is the PLL clock. So we have two choices to run the microcontroller. Either we use the oscillator clock, which is the clock coming from outside, or we use the PLL clock, which is the clock, the oscillator clock that is scaled using the phase lock loop block. So these are this is the main thing that we talked about last time, and we talked kind of in a detail regarding the phase lock loop and how to use it, how to configure it. Excuse me, how to configure it to be used as the system clock. And we said that this block and every single every peripheral device or every input-output port or every single configurable feature of the microcontroller is usually done through a set of registers. And here we have the registers related to the operation of the CRG block. We talked about some of them last time, and one of these registers is the clock select register or the CRG select register, which has several bits through which we can configure the features of this block, or it contains some bits that indicate the status of this block. For example, we said this bit, which is the PLL select bit, is used to select whether the PLL clock is used as the system clock instead of the oscillator clock. So this is one of the special registers related to the CRG block. And as we said, we talked about how to configure the phase lock loop and how to the phase lock loop and how to use it as the system clock. And we said that there are three registers, three new registers related to the PLL operation, which are the reference DFDV register, sorry, the refdev register, and the send register, which are basically factors that you can use to scale the oscillator clock into the PLL to find the PLL or to generate the PLL clock of certain frequency. And so here we can store 6 bits, and here we have 4 bits for the value of refDV. We also talked about this special register, which is the Pll control register, through which we can turn on the PLL block using this bit. So this bit is initially 0, which means or it is on reset, it is 0, which means it is the PLL is turned off. The PLL block is turned off. Excuse me. So if you want to use the PLL to scale the oscillator clock, you need to make this bit 1, and we saw how to do that last time. Also, there are other blocks. There are other bits in this register that are kind of important, and I will talk about them in shortly, which are the CME block bit and the CMSCME bit, which are responsible for the clock monitor sub-block and the self-clock mode enable bit. So remember this register, PLL control register, with these 2 bits to be discussed shortly. Also, we said there is another register, which is the CRG flag register, which has basically a set of status flags or bits that tell us something about the status of different aspects related to the CRG block. And among these bits are the lock blocks, the lock bit and the lock IF bits. The lock bit, we said, basically is a status bit that tells us whether the PLL has reached or has converged or has approached the frequency that we configured it to work on. So as long as the PLL is far away from that frequency, this bit is 0. Once it is within certain tolerance of the desired clock, this bit will be automatically set by hardware to 1. Now, if for some reason the PLL frequency is changed, let's say due to noise interference, due to some change in the supplied voltage, then this bit will be reset also automatically. Now, this transition between 1 and 0, between the 2 states, lock state and unlock state, or they call it acquisition state and lock state, will automatically set this flag, which is the lock IF flag, the lock interrupt flag. So this flag will be automatically set every time the PLL switches between the lock mode and the unlock mode, or the lock mode and the acquisition mode. And the acquisition mode implies that the PLL has not converged to the desired frequency, and the lock mode, basically, the PLL has converged. Now, this bit is called the interrupt flag because as soon as this bit is set, we can configure the PLL to interrupt the microcontroller to do something related to the event of frequency change, whether to converge or whether convergence or divergence. And in order to enable this kind of interrupt, which is the PLL lock interrupt, we need to go to the CRG interrupt enable register and set this bit. So this is the local enable bit for the interrupt enable related to the lock status of the PLL of the phase locked loop. Now, but in order to activate this PLL, we need also to clear the I bit, if you remember, which is the enable bit for all maskable interrupts. So the PLL interrupt is maskable. This is the local interrupt enable bit, and this is the global enable bit, which is the I bit. And probably in the second homework, I will ask you something about related to the PLL interrupt. So what we did next was, or before I go, what we did next, I need to talk a little bit about this important thing. So we said this is an interrupt flag or interrupt status flag for the lock event. And here, if you go to the description, this is the PLL lock interrupt flag. 0 implies that there is no change in the lock bit. 1 implies that the lock bit has changed, either from 0 to 1 or from 1 to 0. However, what I'm interested to talk about here is this. It tells me that this flag is set to 1 when the lock bit status bit changes. So this flag or this bit is automatically set to 1 whenever the lock bit changes from 1 to 0 or from 0 to 1. So now this is very important. If you enable the interrupts, this interrupt, as soon as this flag is set, the microcontroller will be interrupted as soon as it finishes the execution of the current instruction to execute the interrupt service routine that you write for the PLL interrupt. Now, once the CPU finishes executing the interrupt service routine, it will go back to the main program or to the normal operation mode. Now, there is a problem here, or there is one important thing that we need to point out here, is that this flag, which is the lock IF flag, is not cleared automatically. It is set automatically as soon as the interrupt event occurs. But however, it is not cleared on its own. It's not cleared automatically. So what will happen once the CPU finishes executing the ISR of this type of interrupt? It will be interrupted again if you don't clear this bit. So this is very important thing, and it is a common practice in all microcontrollers and all microprocessors, is the fact that interrupt flags are not cleared by themselves. They are set automatically by the interrupt circuit, but they are not cleared by the interrupt circuit. It is the responsibility of the programmer to clear this flag before the main program, before the CPU resumes execution in the main program. And how to clear this flag? Basically, it tells me this here. This flag is cleared, can only be cleared by writing 1 to it. And this is the same thing for all interrupt flags in this microcontroller. The only way to clear this interrupt flags is to write 1 to these bits. So it's very important. Interrupt flags are not cleared automatically. They are set automatically, but they are not cleared automatically. So it is your responsibility to clear the flag by writing a 1 to it for this type of microcontroller before you return from the interrupt service routine, before you come back from the interrupt service routine. Otherwise, if you forget to do that, the microcontroller will be interrupted again, because as long as this flag is 1, the microcontroller will be continuously interrupted, but it will always finish the ISR, go to the main program, it will be interrupted again. But this is called false interrupt, because this interrupt request has already been serviced before. So this is very important. We didn't have something like this when we talked about the, if you remember, the IRQ and the XIRQ interrupts. These interrupts, they don't have interrupt flags. They don't have interrupt flags, so that you don't need to worry about clearing their flags in their interrupt service routine. I will not go into the details why they don't have interrupt flags, but these interrupt sources, the IRQ and the XIRQ, they don't have interrupt flags. While most of the interrupt sources, Muscadine interrupt sources in this microcontroller have interrupt flags that have to be cleared in your interrupt service routine before you go to the main program, So this is very important regarding the interrupt flags. So we had an example. We wrote some code in order, we wrote a subroutine, which is called set CLK, in order to use the PLL clock. So we said basically we need to figure out the values of the scalars, these scaling factors. Then we turn on the phase lock loop, enable the PLL or turn it on by setting the PLL on bit. Then we said we can't immediately switch to the PLL clock because we need to wait until the PLL clock has converged to the desired value. And how do we know that it has converged? When the lock bit in the CRG status, CRG flag register, it changes from 0 to 1. Initially it is 0. So once the PLL has reached the desired frequency, this bit will be set to 1. So here we have some kind of pulling. This is pulling. We are pulling the lock bit in this register, and as long as this bit is clear, we will branch to the same instruction. Otherwise, once it is set, we go to the next instruction where we set the clock, the PLL clock as the system clock by setting the PLL select bit to 1. Yes, Marwan.
دكتور مش كنا نحكي بالinterrupts we always use in the end of the interrupt بيكون في ال RTI.
Yes.
مش ال RTI هي it's responsible of clearing the
لا.
enable flag of the local interrupt?
No. As I said, this is a common practice. In most microcontrollers, the RTI or return from interrupt or whatever is the name of the instruction or the mnemonic of the instruction, these instructions, they don't clear the interrupt flag. It is your responsibility as a programmer to clear the flag. Okay?
Okay.
I will not go into details why and why not. So we'll just take it like this. Okay, then we saw how to do that also in C, and we talked in details. So let's now go and discuss some of the remaining features in this block. And one of these features, if we go back to the block diagram of the CRG block, this block, we have this, the clock monitor sub-block, which is inside, if you look carefully, it is inside the oscillator block, which is the block that receives the external clock, whether from external source or from the external crystal oscillator. So what is the purpose? What is the function of this clock monitor? Basically, as the name implies, this block monitors the incoming clock from outside. So if there is a problem with the clock, you can enable this sub-block. By default, it is not enabled, but you can enable it to watch or to monitor the oscillator frequency or the incoming clock. And if there is some problem, such as the clock is turned off for some reason, you can configure this block to do something. And this block basically can do one out of two things, can be configured to do one out of two things. Either it resets the microcontroller if there is no clock edges are detected within certain time, with a certain time period. So there is an RC circuit inside this block. Once this RC circuit, the time elapses equals the time constant of this RC circuit, and there is no clock, this clock monitor subblock can be configured to reset the microcontroller. Okay, the other option is you can configure the microcontroller such that if the clock monitor detects a problem with the incoming oscillator clock, it switches to the self-clocking mode, or the SCM mode, in which, as we said last time, the microcontroller will clock itself using an internal clock, but at a very low frequency, So how to enable these features? If we go back to the Pll Control Register, as we said, mentioned earlier, we have this bit, the CME bit, or the clock monitor enable bit, which basically through which you can disable or enable this feature, which is monitoring the clock. By default, it is disabled on power on or on reset. Now, how to decide what happens if there is a failure in the oscillator clock if the clock monitor is enabled? Basically, this is done through this bit. If this bit is 0, which is by default 0, and the clock monitor detects a problem with the clock, this will result in a resetting the microcontroller. However, if you enable the self-clock mode using this bit by setting this bit to 1, if there is a problem with the clock monitor will basically forces the microcontroller to go into self-clock mode, in which, as we said, the microcontroller is basically clocked internally without relying on the clock that is coming from the outside. Okay, so this is very simple, which is the clock monitor. This is another feature that is available in the CRG block. Yazan?
دكتور the same scenario لو كان يعني ما عنده كلوك ممكن اشغل المايكرو على نفس يعني سيلف كلوك.
يعني you mean if you don't want to clock the microcontroller from some external source, can you always clock it internally? Yes. If you power on the microcontroller and if there is no clock edges, as you see here, and this will happen if you don't connect any clock to the microcontroller, you can enable the self-clock mode.
All right, yes.
So if that bit is set, then basically you can enable it.
Come.
Okay. Another feature that is inside this this CRG block is the computer operating properly. Computer operating properly, or COP for short. COP for short. In some other microcontrollers, they call it Watchdog Timer. They call it Watchdog. I can't write on the screen. They call it Watchdog Timer. And basically, this feature allows us to monitor the behavior of our program while it is running. And what does this feature do? Basically, it is a timer that can be enabled such that if the timer overflows, it resets the microcontroller. So this is the basic idea of the COP or Watchdog Timer. It is a timer, and that can be enabled. And once enabled, and the timer reaches its maximum value, or in other words, it overflows, this event will reset the microcontroller. Now, why do I have such feature? Well, how can I take advantage, or how can I use this feature? Where is this feature useful? Where can it be used? Basically, the Watchdog timers or the COP timer can be used to reset the microcontroller in abnormal conditions or in abnormal operations. Imagine that you have used your microcontroller and you have wrote and loaded some program in your microcontroller, and let's say this is the start of your program, and this is the let's say branch start, whatever is the program, regardless what is inside this program. Now, as long as everything is okay, your microcontroller will keep executing this program over and over. Now, imagine for some reason, due to noise, due to overheat, that your program got stuck at this point. Got stuck. So the microcontroller is no longer able to continue the execution due to overheat, due to some noise, or whatever. So what is the solution for this? How can we get out of this stuck state? Basically, what we can do, as we do with most of our devices usually, is when they don't respond to us, we reset them. We turn them off, then we turn them on. In the case of microcontrollers, we can reset them, or we can turn the power of them on. However, imagine that this microcontroller is part of an embedded system that is flying in space, or part of an embedded system that is buried inside the ground. How will you reset the microcontroller? How will you turn off the power, then turn it on? You cannot do that. It's very, very expensive, or almost it could be impossible. So here comes the responsibility of the Watchdog timer, or the COP. The COP basically is a timer that is running in parallel to the execution of the program. So the COP is, if you enable it, you can configure it to reset the microcontroller after some time. Let's say after 200 or 20 milliseconds. So every 20 milliseconds, the COP will reset the microcontroller. Okay, so now imagine this scenario. If the COP is configured to reset the microcontroller every certain period of time, let's say 20 milliseconds, and the microcontroller got stuck here. What will happen after 20 milliseconds of being stuck? The COP will overflow and it will reset the microcontroller into and will force it to start from the beginning. Okay, so this is the basic idea. The COP, as the name indicates, computer operating properly. As long as your computer is operating properly, there will be no effect. There should be no effect of this timer or this event. It will not reset. However, if your program behaves in a normal way, such like this scenario, it gets stuck, then this COP or this timer can reset the microcontroller. Now the question is, how does the COP or the Watchdog timer know whether your program is stuck or not? How does it know? It doesn't actually. It doesn't. All what it does, it resets. If it is enabled, it will reset the microcontroller. That's it. So what is the idea behind this question? The idea is, if you decided to use the COP in your program, in your system, then in other words, you enabled it, you need to make sure that as long as your program is working normally, you need to reset or to clear this timer. You need to prevent it from resetting the microcontroller because your program is working normally. And this COP does not know whether your program is stuck or not. So how to prevent the COP from resetting the microcontroller as long as your program is running normally. Basically, this is what we have here. To prevent the COP from resetting the MCU under normal conditions, basically we need to reset the timer. In other words, we need to make it count again from 0. And this is done using this approach. We need to write 55 followed by AA to the ARM COP register every less than 20 milliseconds, for example. So if the COP is configured to reset every 20 milliseconds, we need to do some calculation to know, for example, this section of my code will take, let's say, 19.5 milliseconds. So at this point, I need to write move B $55 ARM COP followed by move B $AA ARM COP. So this is kind of a token that is sent or written to this register. So this, what is the ARM COP? It is a special register related to the COP operation. So we need to write this to reset the microcontroller because our program is not working normally. So if we do this, we reset the COP and it will start counting again. And we might need to do this over and over every sometime in order to prevent the COP from. So this, we need to do some calculation. If this has to be less than, let's say, 20 milliseconds, this has to be less than 20 milliseconds. Okay, so this is the basic idea. Now, how to configure the COP feature, how to enable it, how to determine or specify the reset period. After what time the COP should reset the microcontroller. All of this is done using the COP control register. The COP control register, which is shown in the following slide. Basically, it has, I'm interested in these 3 bits only, which are CR1, CR2, CR1, CR0. And basically, these bits specify whether the COP is enabled or not. And if enabled, they specify what is the reset rate or the time rate select. So if the value is 000, then the COP is disabled. So you can enable it by writing some non-zero value to these 3 bits in your program at the beginning of your program. Down under, we have other possible values. For example, 010, it tells us that it is equivalent to 2 to the power 16. What is meant by 2 to the power 16? 2 to the power 16 means that the COP timeout, let's say, the COP will time out after 2 to the power 16 cycles. So this is the number of clock cycles from the oscillator clock. So this is the number of OSC clock cycles. So this should be multiplied by 1 over F oscillator, or the main frequency, or the main clock that is coming into the microcontroller. So even if you are using the PLL to clock the system, the COP will use the main oscillator, will use the frequency that is coming from outside the microcontroller. So this is 2 to the power 16. So you simply can calculate this time, which is this time, and decide how often you need to put these instructions to reset the COP, to prevent it to reset the microcontroller. As long as your program is running normally, you will always get to this section of code and this section of code and clear the COP. If your program gets stuck here, then you will never be able to reset the COP So the COP will overflow and it will reset the microcontroller. So this is very common feature. You usually most of the mid-range and high-range microcontrollers, they have Watchdog timers or COP, computer operating properly timers, to reset the microcontroller whenever the program is not executing properly. All right. Now, this kind of details, you can go through it. Writing any value other than this or this into the COP register will reset the microcontroller. So this is just a note. Make sure to write this sequence of instructions, 55 hexadecimal followed by AA hexes. Okay. So this is another feature. So we talked about the clock. In the CRG block, we talked about the clock functionality. We talked about the PLL. We talked about the computer operating properly, the clock monitor, the self-clock monitor mode, and there are other things to talk about. And I picked these, which are the low power modes, which are basically in which we talked a little bit about them last time. We said that we can put the microcontroller into waiting mode or into stop mode. And basically in these modes, we turn on all of the system clocks or some of the system clocks. And what is the purpose of turning off some clocks? Why do we need to turn all the clocks or some of the clocks off while the microcontroller is running? Yes, Muhammad.
هسه السي او بي يعني شيء منيح انه يكون عندي في السيستم. طب ليش هو انه انا لازم اعمل له انيبل؟ ليش مش باي ديفولت يكون معمول له انيبل؟
لانك اذا عملت له enable, if you enable the COP, this implies that you need to take care of it. لازم
طب اوكي عادي بكتب التو انستركشنز الخاصين فيه، بس انه الموضوع راح يكون تو complicated يعني من هذا الباب؟
لا it's not too complicated, but you need to take care of the COP. You need to time your program. You need to know how often and where to place the reset instructions for the COP.
عشان ما يوصل التايم اب وتايم اوت ويعمل اوكي.
Exactly. It's not only one occasion where you write these two instructions.
فهمت عليك.
You need to write them every 20 milliseconds of your program lifetime, let's say.
اوكي شكرا دكتور.
مروان.
دكتور you might need to يعني the timers need to be turned off عشان مثلا if you're in the waiting mode ما بدك يرجع البرنامج يبلش من اول جديد. You just want to wait for a command.
You are answering my question. And why do we need to turn off all the
timers? Yes.
Or the clocks or some of the clocks inside the microcontroller. In other words, why do we need the stop mode and the wait mode?
Yes, exactly.
Yeah, and your answer is?
No, sometimes مثلا you want to be in the waiting mode to wait for a command, but you don't want the PC to be reset to the beginning of your program. So you don't want to enter the reset mode.
Not really. Actually, as the title implies here, it's low power modes. These two modes, the wait mode and the stop mode, they are called low power modes because in which we turn all or some of the system clocks. And when you turn off the clocks, basically you are killing the operation of the microcontroller or part of it. And when you kill operations or when you stop operations, basically you reduce the power consumption. So sometimes your system might not need to be up and running all the time. For example, imagine that we have, let's say, a weather station in which the system should measure the temperature, measure the humidity, measure the wind speed, take the readings, send them to the base station, and then it should wait and take another reading after 1 hour. So what to do during this 1 hour? It is not
it's not efficient to keep the system powered on, right? Or consuming power. So you just need a mechanism to reduce the power consumption during this time. And when the system is supposed to go back to normal mode, you go out from, let's say, the waiting mode to the normal mode. So basically, the waiting mode and the normal mode, they kill some or all the clocks, the operating clocks in the system to reduce power consumption. Especially, this is very important, especially if the system is powered by batteries. If the system is powered by batteries, okay? So I will not talk a lot about the details. Here we have the wait mode. It talks about the wait mode, and here it talks about the stop mode. I will leave them to you to read about the details of them. It's just these two slides. But what I'm interested in is you have something like this. If I want to draw a state diagram, this is normal operation where the microcontroller is up and running. And let's say we have the wait mode, and we have the stop mode, okay? And if you go back to the wait mode, how does the microcontroller go from the normal mode to the wait mode? Basically, if your program executes the wait instruction. So this is a state diagram to describe the operating modes. How does your program go from normal mode to stop mode? Basically by executing the stop instruction. So this is how to go into the low power modes. And what happens in the wait mode, what happens in the stop mode, I will leave him to you. What clocks are turned on, what clocks are turned off, I will leave him to you. What I want you to know is now, suppose that you put your microcontroller into wait mode. How can you get out of the wait mode? How can the microcontroller get out of the wait mode? How can the microcontroller get out of the stop mode? Basically, in the wait mode, some of the system clocks are turned off. Basically, the E clock is turned off, so your program is not being executed. It is paused. The execution of your program is paused. However, all sources of interrupts, if enabled, are still working because their clocks are not disabled. So going out of the wait mode, for example, occurs if you go here to exit the wait mode. Any maskable interrupt or non-maskable interrupt and resets will take you out of the wait mode. So for example, if you enabled the PLL interrupt, the PLL lock interrupt, and the PLL frequency changed. So this type of event will force the microcontroller to go out of the wait state if it is already in the wait state. So this is how to get out of the wait state if an maskable interrupt occurs, or a non-maskable interrupt occurs, or some sort of reset also occurs, such as what? You input 0 to the reset pin. So this definitely will reset the microcontroller and everything start from right from the beginning. Or if you have enabled the COP or the Watchdog Timer, it will reset the microcontroller if it overflows, even if you are in the wait mode, because when you go to the wait mode, the COP is still up and running, so it will reset the microcontroller when it overflows. And this is very useful. For example, in the example we just talked about, if you want your system to do something at this moment, then go into sleep mode or wait mode to reduce power consumption. You want to wake it up
how you want to wake your system up to go back to normal state. Basically, if you enable the COP and configure it to reset the microcontroller after this period of time, then you can achieve that. Now, the same thing for the stop instruction, how to get out. Basically, this is done only using the IRQ interrupt or the XIRQ interrupt. Other non-maskable or maskable interrupts cannot reset, cannot get you out of the stop mode, because in the stop mode, all system clocks are turned off. Nothing is operating. So only these two signals or these two inputs can get you out of the stop mode. Okay, the details I will leave them to you. Okay, so most of what I said is on these two slides. So this slide is about the wait mode, which is a low power mode, and this one is about the stop mode, which is more power efficient than the wait mode, because in this mode all the clocks are turned off, and also of course here resets can turn off, can get you out of. There are other details on this slide, and if you are interested, read them. Okay, what happens if you go out of the stop mode and on an interrupt and so on. Go through them. Okay, the last thing or the last feature that we want to discuss here is the real-time interrupt. Yes, Muhammad.
دكتور الويت مود والستوب مود مش احنا مش عارف مش حكينا انه لهم بت خاص فيهم.
No, yes, they have special bits. They have special
طيب
bits.
اوكي. ليش ما السيستم يكون عندي اوتوماتيكلي انه انا اذا صار عندي هيك خلص اروح على البت الخاصه في الويت مود واعملها زيرو عشان انا go to normal operation.
This is a design issue, but the bits that are related to the stop and wait mode are related to what happens to some features in the microcontroller during the wait mode or during the stop mode. They are not used to turn on or turn off the power, the wait mode or the stop mode. What activates the wait mode or the stop mode is the sleep, is the wait and the stop instructions respectively.
تمام.
Okay.
تمام.
Okay. The last feature that we want to discuss in this CRG block is the RTI feature or the real-time interrupt, which is basically one of the maskable interrupts sources in this microcontroller. And what is the idea of this interrupt? How is this interrupt event generated? Basically, the real-time interrupt basically is a timer. We have a timer. If you go back to the block diagram of the CRG block, here we see here the RTI. We see the RTI, which is dependent on the incoming clock, whether the oscillator clock or the phase lock loop clock. And what does this sub-block do? Basically, what does it have inside it? Basically, it has a timer or a counter that counts, and you can configure the period or the time after which this timer will time out. And if you enable this, the interrupt of this block, when this timer times out, this will interrupt the microcontroller. So basically, it is an interrupt source that can be enabled and used and configured to interrupt the microcontroller periodically. So the main function is to generate periodic interrupts, and that's it. So there is a counter inside the CRG block that counts for a certain period of time, and this period of time is configurable. Once the timer reaches the maximum or reaches this time or times out, in other words, this event can be used to interrupt the microcontroller. Now, this is a Muscadine interrupt. In order to enable it, you need to go to the CRG interrupt register, which is shown in 6.11, which is the same register that contains the PLL lock interrupt flag, interrupt enable, I'm sorry. If you go back here, this is the CRG interrupt enable register. So this is the bit that is responsible or that enables the real interrupt locally. And of course, because it is maskable interrupt, in order to use it, in order to enable it, you have to set this bit to 1, and you have to clear the I bit by writing CLI in assembly, or in C by writing enable, if you remember, enable interrupts, okay? Enable interrupts. So this is very simple. It is an interrupt source that can be used to interrupt the microcontroller periodically. You can enable it using this special bit, the RTIE bit that is in this register. Now, how to determine how often does this interrupt happen or occur? Basically, we have RTI control register, and in this register, you can store some value, and this value will specify the rate at which your interrupts are generated, or will specify how often your interrupts will be generated, or the period of time, in other words, after which or every which we generate an interrupt. If we look at this RTI control register on the following slide, this is the RTI control register. Seven bits are used, which are from RTR 0 up to RTR 6. And the value stored in these bits determine the time out period of the RTI interrupt, of the real-time interrupt. And this is shown in this table. This table tells us the period, the timeout period of the real-time interrupt, the timeout period of the real-time interrupt, and it is straightforward. For example, here it tells us if we have here the column, the value in the column are the bits RTR 0 through 3, which are the least significant 4 bits in this register. So the 4 bits here are the columns which determine the divisor, of the oscillator frequency. And here, the upper 3 bits, which are RTR 4 through 6, which determine the multiplier. For example, if the value that is stored in this register, which is the RTR or the RTI control register, so these 6 bits determine the timeout, let's say, period. So the lower 4 bits determine the divisor, the upper 3 bits determine the multiplier. So let's assume we have here a value of 1100, and here we have, let's say, 010. So what is the timeout period? What is the RTI timeout? How often will the RTI, will the real-time interrupt the microcontroller? Basically, you need to go to this table. We will have the oscillator clock, or let's go to the table. So here we have 1, we have 1100. So it is 1100, which is divided by 13. Okay, and we have 010 in the columns. So we have here 010. So if we look here, we have 13 times 2 to the power 10 cycles. What is the unit of this number? It's not second, it is cycles. And what is the cycle time? It is the oscillator clock. It is the oscillator clock, which is the clock that is coming into the microcontroller. So this is also multiplied by 1 over FOSC clock, which is the clock that is coming into the CRG block. The same case we had for the COP. The COP, the number of cycles are basically the cycles of the oscillator clock. So this gives you the timeout period of the RTI. We have some examples here. Here we have, for example, let's assume, if we assume that the oscillator clock is 16 megahertz and the Rti control register contains 59. This is similar to what I did here, but different example. Then we will have 10 times 2 to the power 14. If you take 59, which means the lower 4 bits are 1001. So we have 1001, which is this. Sorry, which is this. And the upper 3 bits will be 101. So it is 5 here. So the multiplier for the oscillator period is this. 10 times 2 to the power 14, which is 16, which is 163,084 cycles. And in time, in seconds, it is this value divided by the oscillator frequency or multiplied by the period of the oscillator, which is 10.24 milliseconds. This is another example and similar to what I did here. Another example is also given here if you want to check it later. So basically, you can control the timeout period. However, the largest value is here, is this point. So the largest multiplier to the oscillator period is basically 16 times 2 to the power 16. This is the largest time or the largest timeout period for the real-time interrupt. Okay. So where we might need to have something like this, where might this be useful? As we said, we might need, for example, to put our microcontroller in low power mode, and then we want to wake it up after some time. So the real-time interrupt might be useful in this case. Or your program might be running normally, and you want to remind your microcontroller while executing your main program to do something every once and a while, every periodically to do something. And to achieve that, one way to do it is your real-time interrupt. So it is kind of an alarm that runs periodically, like your alarm, the alarm that you set every day, okay, to wake up, to go to work or go to school. You set it at 7 a.m. So every day it rings. So it's kind of a real-time interrupt. Every day at 7 a.m. it interrupts your sleep. Okay, so this is something similar. Now, how to program the real-time interrupt in Code Warrior? Nothing new. Similar to how you program other types of interrupts. But the thing you need to do before you enable the interrupt is basically choose the appropriate timeout period, enable the RTI interrupt in the CRG interrupt register, write your interrupt service routine, write what has to be done when the RTI occurs, when the real-time interrupt occurs. But always remember, as we said earlier, to clear the RTI flag that is available in the CRG flag register, which is the same register that has the lock IF flag. There is the RTIF flag. You need to clear this flag in your interrupt service routine before you go back to the main program. Otherwise, another interrupt will be serviced, which is a false interrupt. Here we have examples, 2 examples, I guess. Write a C program to count the numbers 0 through 9 on the 7-segment display connected to port H in the Mini Dragon port. So the Mini Dragon board that we have does not only have the microcontroller, it has other devices around it. One of these devices is a 7-segment display that is connected to port H. That is connected to port H. So if you want to do something with a 7-segment display, when you have the board, you don't have to connect an external one. There is one that is already connected to the microcontroller. So on this 7-segment display, we need to have a counter that counts from 0 to 9 continuously. So it just keep counting. And the count is incremented every 0.0655 seconds using the Rti interrupt, So basically, we want to write a program that uses the Rti interrupt to increment the value that is displayed on the 7-segment display every 0.0655 seconds. Okay, so we need to use the Rti. So the very first step is to determine what is the multiplier for the Rti interrupt. So we do some calculation. So the Rti period is this. So we say, and the oscillatory clock, we assume it's 16 megahertz, which is basically the clock that is available in the Mini Dragon board. So we say that 0.065, which is this, the timeout period, is basically x, which is the number of cycles multiplied by the period or divided by the frequency. So if you do the math, x, which is this, has to be 2 to the power 20. 2 to the power 20, 2 to the power 20, which is, if you write it differently, it is 16 times 2 to the power 16. In other words, it is 2 to the power 4 times 2 to the power 16, which is 2 to the power 20. If you go back and look for this value, it is this value, 16 times 2 to the power 16. So you need to store in the Rti control register, you need to store 111, 11111. So 7 ones have to be stored. So the Rti control register should be set to this value, which is the largest multiplier or the largest scale. So here we have the C program. The program is written in C. So let's go to this is part of the program, but I will go to the main program. In the main program, we configured port H as output, and we output to it my 7-segment of count of CNT. This is CNT. It is a variable that is used to index this array. And if you go back, this array is basically this. My 7-segment is this array, which is a string that contains these. What are these? These are the 7-segment codes. These are the 7-segment codes to display the numbers on the 7-segment display. So we have port H, so this is the PTH0, and this is 1, 2, 3, 4, 5, 6, 7. So we have 7-segment display like this. So this is, if this is A, I guess this is A, B, C, D, E, F, G, this is G, and something like this. So what we have here are the 7-segment codes that we want to send out to the 7-segment display to turn on different segments of the display. Assuming that the display is common anode here, which is the same as I drew here. However, the 7-segment display that is on the Mini Dragon board is common anode. It is common anode. So we want to take the complement of these. So that's why we had this nut here. This nut in order to change or complement the 7-segment code. So what we are doing here, basically, every time we want to display a value, which is from 0 to 9, we go to this array and get the 7-segment code of 0, the 7-segment code of 1, the 7-segment code of 2, 3, 4, 5, and so on. Okay, so initially we output 7-segment of 0, which is the 7-segment code for 0. So all segments will be turned on. Then we configure the RTI interrupt. We say enable interrupts. We write the multiplier. We enable, we set the RTIE bit to 1 to enable the RTI interrupt locally. Then we write this statement, which is basically will be replaced by ASM, as we said, CLI, right? Clear interrupts, and then while 1. So note that the main program, once it configures the features, required features, it only goes into an infinite loop. So what will get us out of this interrupt loop, this infinite loop, is the RTI interrupt. Because it is enabled and it will overflow every 0.0655 seconds, we will be, the microcontroller will be interrupted, so the execution moves to the interrupt service routine related to the RTI. So I called it RTI ISR, and this is, we know how to program interrupts in C. We need to put the interrupt number and use the keyword interrupt, and this number can be found in the interrupt vector table. And what to do, what service should this interrupt service routine provide? Basically, it needs to increment the count value. We started from 0, so now we need to move to 1 because 0.0655 seconds has elapsed. So this is what we do here. We increment the count value, and then we check if the count value is greater than 9, then we have displayed all the numbers, and we have reached here. We have displayed we have displayed 9 on the 7-segment display. So we need to reset it. So we reset it. Okay, and in all cases we output the new value. And the last thing we said before we go back to the main program, the RTIF flag has to be cleared by writing 1 to the RTIF bit, to the RTIF bit. And here we have 80, which means we are writing 10000000. And this one is basically the location of the RTIF flag in the CRG flag register. Okay, so this is very important source of interrupt. It can be used in many applications, so you need to pay attention to it. Now, what is left, I will leave it to you also, is another example which considers this case. What if you want the RTI period to be greater than 0.0655 in this case, or greater than 16 times 2 to the power 16, right? Times 1 over F oscillator. How to make that? The same example is modified, is changed to take advantage of what we call software post-scaling. Software post-scaling. Look at it, and we can discuss it later if you don't understand. Okay, so this is how to extend a modified example, how to take advantage of software scaling. And there is also another example that uses the RTI. I will also leave it to you, which is similar to what we did. We didn't do it actually, but we saw this example, which is 7-segment multiplexing. But at that time, we used software delay in order to do the multiplexing. Here, he is using only the RTI interrupt to determine which of these displays is enabled in order to display the value. يزن بسرعة سؤال سريع عشان ناخذ الكويز.
دكتور، سؤال بخصوص الانتربت، بزبط اعمل كول للانتربت بدون ما اكشوال انتربت صار؟
كيف يعني؟
يعني مثلا انا بالكود تبعي بحكي له مثلا برانش هذا الانتربت سيرفيس روتين.
يس يس اوف كورس.
اوكي.
لانه في النهايه هو زيه زي مين؟
السيرفيس روتين يس.
زي انتربت سيرفيس روتين. بس شو اللي راح يفرق معك؟
انه هناك باي يعني اكسترنال او اكشوال
هناك
سورس.
يس هناك الستيمولاس هو هاردوير ايفنت، بينما هون الستيمولاس صار عندك سوفت وير ايفنت. اوكي.
اوكي.
وبدك تعرف انه اذا انت سويت كول لانتربت سيرفيس روتين في نهايته راح يكون في ار تي اي انستركشن مش ار تي اس انستركشن. والفرق بين الار تي اي والار تي اس انستركشن انه الار تي اي انستركشن راح تسوي كلير، راح تسوي انيبل للماسكبل انتربتس، صح؟ فاذا انت اصلا مش مسوي انيبل للماسكبل انتربتس راح يصير لهم انيبل وانت اصلا مش مسوي لهم انيبل. تمام؟
يس تمام.
اوكي. طيب عشان ما يضلش معنا وقت، خلينا نفتح الاي ليرنينج اذا سمحتوا. خليني انا بدي نفتح الاي ليرنينج على صفحه الماده على الاي ليرنينج اكيد. اوكي. هلا على الفيرتشوال كلاس روم، على الفيرتشوال كلاس روم سيكشن في خليني بس اسوي له enable show في quiz 1. if you did not see it just refresh your browser and I want everybody to confirm that they were able to log in into the e-learning and start the quiz. So everybody has logged in.
Should we begin attempt?
Yes, begin. If you were able to log in, just start your quiz. Yes, please.
Started.